Good morning, class. Today we're going to work on chapter 21, electric forces and fields. Okay, so Mr. Whitaker. Mr. Whitaker.
Hey, hold up. She want me to solve this problem.
Excuse
right
me?
quick. Yeah, hold up. Oh, that G right there, 9.8. That look like ain't that supposed to be like 5.6 or something like that?
You mean that's not correct? Could you where are your notes? Can you please pull up your notes? We went over this yesterday.
Oh yeah, you're right. I do got my Hey, hold up, bro. My class, bro. Hold up. Yeah. But that Lamar. Yeah. Look, show y'all something because I know what I'm doing. We gonna label that 1. We gonna label that 2. We gonna label that 3. Man, that's first step. I'm not doing nothing else. You know what I'm saying?
Excuse me, mister?
I'm not doing nothing else. Yeah, that was it. You know. I do.
Mr. Whitaker.
Hello? Yeah, you know I got a party this weekend.
I will have to get Victoria Livingston to help me with this.
Alright, so the next step would be to do a free body diagram of which charge you're going to choose. And for this one, I want to choose charge 1. Okay? Alright.
Thank you, Victoria.
So the first step would be to draw a free body diagram. So step 1. This is charge 1 because we're going to work with charge 1. You're going to have force coming this way. You're going to have a force coming from this direction. And then you're going to have a force coming that direction. And then this one. So let's label these forces. This one is gravity, of course. So you're going to say mass times gravity. And G, which is already given to us in the problem, is 9.8, as always. So then, this one right here, since we have this diagonal force, we have to break it up in 2 components, right? X and Y. So this is going to be T. This is going to be Tx, which is equal to T sine theta. And this is going to be Ty, which is equal to T cosine theta. So lastly, our last force is this one. We're going to call it F of C. So one thing that we learned last class was about equilibriums. And there's 2 types of equilibriums. There's static equilibrium and dynamic equilibrium. The difference between the two is that one is moving and then one is not. Static is not moving and dynamics is moving. But both are equal to 0. The sum of all the forces are equal to 0. So if we're going to sum all these forces up in the x and y direction, we would say that when you sum f of x, you would get 0, and that would be equal to this one and this one. So our sign convention is going to be to the right is positive, so that means it's going to be T sine theta minus FC is equal to 0. For our sign convention for the sum of all forces in the y direction, it's going to be 0, and up is going to be positive. So then that would be negative mg plus T cosine theta is equal to 0. Okay, so when we combine these 2 equations, we get something similar to this. Let me show you. We get tangent theta is equal to FC over mg. And the reason why we don't have t anymore is because when you set these, when you divide this one, when you have this one over that one, you'll have 2 t's, and so the t's will cancel out.
Victoria.
Huh?
What
did I do wrong? What did I do wrong?
You're doing everything right.
Okay.
But there's some people that don't remember this. Why we have tangent here, and also here, and also just illustrate here so they know where you got this from.
Okay.
For other students that might need to see all the steps.
Okay. Do I keep going? Or?
Yes, you keep going.
Okay, cool. So, you got the tangent FC. So now we need to solve for FC. From this equation, we get that FC is equal to m mass times gravity times tangent of our theta. Now, that is the first half of the problem. Now we need to work on the second half. So, step 2.
Hey, wait. Hold it. Man, the Rockets won last night. Rockets won last night.
Whitaker.
We're going to the
Keep it down.
We're going to the finals.
Keep it down.
Going to the finals. Carry on.
Okay, anyway, I don't even know what's the rock. Okay, anyway, step 2. So, step 2, we then sum up the forces. So, for this charge right here, we have 2 forces acting on it. We have the force from this positive charge and the force from this positive charge. So therefore, this means that Fc is equal to F of 1 on 2 plus F of 1 on 3. Now, from our equations that we learned last class, we know what the force exerted from one charge onto another charge is. And that's really easy. It's K times Q1 times Q2 over R squared. So basically, this is the problem for this one, and we just add another one using 1 and 3. So K, Q1, Q3 over R squared. So this R right here happens to be something that they didn't give us. So now we have to search for what R is. And R is basically the distance between the 2 charges. But they don't give us a distance, correct? So now we just have to solve for this X and this X prime. So in solving for those, we know that this is equal to L sine of the theta, which is 39, and this is L sine theta of 39, of course. So basically, our R for this one is going to be the L sine theta, and then our R for this one is going to be 2L sine theta.
And that is because we have from 1 to 2, this is our length, and from 1 to 3, we have twice of that.
Precisely. So now if we plug in L sine theta to both of these and 2L sine theta, we will get that FC is equal to KQ squared over L squared sine squared theta plus KQ2 over 4L squared sine squared theta. Now, since we have 2 equations for FC, we now can set them equal to each other, because what we're solving for after all is our Q's. Set these equal to each other, you'll say mg tangent of theta is equal to KQ squared over L squared sine squared theta plus KQ2 over 4L squared sine squared theta. So we get that Q is equal to the square root of 4L sine theta squared times tangent of theta over 5 times K.
All of the values that we have in these equations are already given and solved for. We have to just, okay, and it is Q is equal to 5.29. All of the values that we have in these equations are already given and solved for. We have to just, okay, and it is